Thanks, everyone, for sticking around. We've got Tim Hawken, who is a software engineer at Google. I abbreviated it. It's actually much longer. And so Tim is actually going to be talking a lot about Kubernetes, probably something that you're potentially very interested in, given the talks from earlier. So without any further ado, thank you for coming, and I'll give it to you.
Thank you very much. Sweet. There we go. Hello, everybody. My name is Tim. I work at Google on the Kubernetes project. You may have heard of it. I was one of the original software engineers on this project. It was one of, I won't say my brainchild, but I'll say I was in the first four. Before that, I worked on our internal systems, Borg and Omega. So that's the perspective I bring into this Kubernetes project. Before I get too far into this, I want to get a quick feeling for the room of what I should focus on. So I've prepared a talk that has way more slides than I can possibly get to. So, quick show of hands, who is very familiar with Kubernetes and skip all the background stuff? Underwhelming. Okay. Sorry, guys. I'm going to focus a little bit on the background, and I will try to get to the fun stuff towards the end. So, a little bit of history. So, Google, we've been doing containers in some form or another for over 12 years. When I joined Google in 2004, they were just starting the beginning of what they were calling containers. So I thought it's instructive a little bit to go through some history. Around about 2002, Google was like everybody else. We had pools of machines that were specific to certain applications, and like everybody who's experienced this, they're inefficient, they're painful to manage, they crash, everybody does their own thing, it's very siloed, it's not good. So we decided, by dictate, we're going to move to shared machines. This is the future. Shared machines are everything. We implemented chroots, ulimits, nice. These are the basic tools that systems like Linux gave us at the time. So we used that to build a very, very archaic form of containers. Now, of course, as you've experienced with shared systems, the minute you put two users on a machine, you have a noisy neighbors problem, and it is a real problem. So this very much limited our ability to scale our system. So, of course, over time, Google gets successful. You guys remember the early 2000s, right? Google did that thing, or that thing. The fleet got larger, and the inefficiencies came to be more and more important. So, of course, the dictate was share harder, right? Find better ways to share these systems. And upon much thought, the decision was, good fences make good neighbors, so let's build better fences. 2006, Google develops C groups. C groups, or control groups, is a kernel subsystem that lets you provide to the processes a set of inescapable bounds. Unlike process groups, P groups, which you can actually just step out of if you want to, C groups are completely non-voluntary. You get put in them and you can't get out of them. And this enables us to do better sharing. Now, at Google, it's important to remember isolation is paramount. It's absolutely everything that matters. All the stuff about namespaces, they're secondary. They don't even really matter. For example, if you go look at this project called Let Me Contain That For You, then you'll see that the very first versions of Let Me Contain That For You don't even have namespace support, right? Let Me Contain That For You is literally our internal container code that we have open sourced. So it landed around the same time as Docker, a few months after Docker. It's not really a competitor to Docker, so I'm not going to spend any more time talking about Let Me Contain That For You, except as an example of what we do inside Google. So over time, our needs changed, the solutions evolved. We made a lot of mistakes on our system. Somebody else made them, not me. And we learned some lessons. So now we fast forward to 2013, and what happens? Docker, right? It wasn't sort of intentional. Docker sort of happened by accident, or at least it was sort of leaked by accident, but it sort of changed everything, right? Anybody in the room not heard of Docker? Yeah. Anybody in the room not used Docker? Exactly. So around the time Docker came out, we saw an opportunity to bring some of what we'd been working on inside Google out into the world. Like, as engineers, we want to talk about what we work on, so we saw this as a great opportunity. So we looked around at our internal systems, Borg and Omega, and we thought, what can we do that the world would appreciate? And this is where we came up with Kubernetes. Kubernetes is an awesome word which you will never forget. It is, literally, it's the guy who drives the boat, the helmsman. sticking with the nautical theme because we like it. But it also happens to be the root of the words governor and cybernetic. So it turned out to be a really cool word for a project, and now you will never forget it because we are the Kubernator. Kubernetes is a container manager and orchestration system. It is inspired by Google's internal systems, but it is not Google's internal system, right? We did not just take what we were working on and drop it on you. We built it from the ground up with first principles, with fresh eyes, to adapt to the needs of what people are doing out in the open source world. We do support multiple cloud environments and multiple container runtimes. It is 100% open source. I won't beat on that drum until a little bit later. The tagline I want you to remember is we're always talking about applications, not infrastructure, not machines. So the title of my talk, I was forced to pick a title. Under duress, I chose pain management. Because who doesn't love a good pain pill now and then? So the first and most important piece of pain that people experience when they start talking about containers is lock-in, right? I have this container, I want to run it somewhere. How do I make sure I don't get screwed 5 years from now? So on the Kubernetes project, we go out of our way to try to make things portable. So specifically, we work on your laptop, we work on bare metal, we work on Amazon, we work on OpenStack, we work on Google Cloud. And if you have an environment that we don't work on, I want to hear from you because I want to make it work. We are 100% open. We do all of our design work in the open. So if you don't like what we're doing, if you disagree with our decisions, you can come and talk to us about it. And the whole system, as Lee mentioned in his previous talk, is modular and replaceable. So if there's parts of our system that you like and other parts that you don't, you can throw away the things you don't like or don't need. Now the goal here is that you write your applications once and you run them anywhere, right? We've seen this before. So I'm going to caveat that with an approximately. But the key takeaway here is that we spend a lot of time in designing Kubernetes such that you don't have to write your applications that know about the cloud provider. We try really hard to inject ourselves in between so that you can write your applications and be divorced from those details. So some examples of this you can see in the way we've designed our network model, the way we've designed our load balancers, the way we've designed our storage subsystem. The next big goal of the system is to avoid coupling. Coupled systems are inherently brittle, and they cause trouble over time, so we wanted to make this a very, very loosely coupled system. We don't want you and your applications to couple to us. So we go out of our way to make sure that all of the abstractions we provide give you the freedom to do what you want to do, not what we force you to do. And you can see examples of this in just simple things like environment variables. You choose the name of the environment variable to expose various bits of information into. We don't choose it for you. That way you don't end up with the word Kubernetes built into your application. The result of all of this, I hope, is that you have portable applications. You can write them in your on-prem data center. You can write them on your laptop. You can lift and shift and move them into the cloud when you're ready for that. So the point here is you don't get stuck. You're not locked into any one particular cloud provider. So now, pain point number 2. Networking. Again, quick show of hands because I want to see who's paying attention. Who has played with Docker networking and found it inscrutable? Yeah, that's a lot of people. So just a quick background for those of you who haven't played it. Docker networking. Imagine a cluster or a network of 3 machines. Docker does what it does, and it picks a subnet for each machine based on what available interfaces are on that machine. Given 3 disjoint machines, it's probably going to pick the same subnet for each of the machines. Now, if I want to talk to containers across these machines, I have to do network translation between them. Whoops, I blew my line. So specifically, look at it in more detail. If the container B wants to talk to container C, it first has to source NAT itself on the way out. It has to talk to a semi-random port that's been allocated to container C. These things have no idea where they are. Worse, if container C restarts, it might get a different port. So now you need to have, first of all, a flag that tells your container what port it's running on. You need to have a service discovery mechanism that lets you do dynamic management of ports. You can't build ports into your applications. It becomes this enormous mess. Every URL you share with your colleagues at work has a port number built into it, and when you paste it into your URL bar, you have to delete the port name because it probably changed in between. And anybody who has played with Google, who's worked at Google, experienced this. So we decided from the beginning of Kubernetes, this is not going to work. This is, in fact, very similar to how Google works internally, and it's a bad model. We don't want to start with this pain. So instead, we took a fundamental assumption that Kubernetes IPs are cluster scoped, that pods can all reach each other directly without source NAT, without port mapping, even across nodes. This is a very fundamental requirement of the system. This means no brokering of port numbers. We don't have an allocated map of which ports you're allowed to use. We don't have to try to enforce that. We don't have to tell your application that I know you're Apache, but you can't run on port 80 because you have to run on port 31622. There's many solutions to how to achieve this. They can be L3 routed with something like Calico and BGP. They can be underlaid like GCE or Amazon static routes, or they can be overlaid with an SDN. There are many valid solutions to this. The net result is all these containers can talk to each other, period. Next pain point, when you want to run things together. So imagine for a moment you've got this cluster. You've got two machines that are packed to the brim. They've got a little space left, and I want to run this job. This job has a file puller. It's my content syncer. It checks out my content from some source repository, and I've got a web server which actively serves that, right? These two things, they really need to run together because running like this is really not very useful. I'll be pulling my files down to one machine and trying to serve them from another machine. That's not helpful. So again, we threw this idea out from the very beginning, and we introduced a concept called pod. Pods are a small group of tightly coupled containers that work together to present an abstraction. They are the atom of our scheduling and placement in Kubernetes. They are how we do resources. They share things like an IP address and a network namespace and IPC and host name, and they can share stuff across volumes. They have a managed lifecycle. They share fate together. If you kill the pod, all of the containers in the pod go away. So let's talk about the next pain point. I'm rushing through this a little bit to get to the interesting parts. Let's talk about storage. How many people here have tried to figure out storage and containers? How many people have been successful? Yeah, that's the one, Adrian. Tell me later. So Docker has this concept of volume, right? Kubernetes also has a concept of volume. We support many types of volume plugins, but we have one primary distinction from Docker's concept of volumes. Our volumes are bound to a pod, which means when your pod is alive, containers in that pod can share stuff across volumes, and when your pod goes away, you can delete those volumes if you want to. Now, you don't always want to. Sometimes you want to run your MySQL, and after your MySQL process is exited, you want to post-mortem it, or you want to shuffle some logs off. So we have a second concept called a persistent volume, and a persistent volume is a higher level of abstraction. This is one of those places where we try to insulate you from your cloud providers. Admins provision a persistent volume, for example, a Google persistent disk, or an Amazon EBS volume, or ... any number of volume plugins that we've got. We now have auto-provisioning in our 1.2 system. These give you an independent lifetime from your containers. So you can create a volume, and you can attach to it and detach from it and reuse it later. And when you're done with it, you're done with it, and the system will release it. Volumes are dynamically scheduled. The idea of claiming some space on a volume gets scheduled onto available volumes, just like we do for processes and pods. Next pane. Container soup. So you've been wildly successful at deploying containers, and you've got a couple of machines that now look like this. What is this? What's going on? How do I group these things together? Now, Lord help you if you zoom out and you've got 8 machines. I didn't even do the picture if you zoom out and you've got 800 machines. But you can imagine that the complexity of managing these microservices at scale starts to get a little overwhelming. So in reality, pods are not, or services are not all the same color, right? They have different identities, and so we can use those identities to help identify them. So your cluster really looks something more like this, right? So in order to help you group and identify containers, we have a concept called labels. Labels are arbitrary metadata, key, value, but you can attach them to every API object in our system, and you can use them to select API objects from our API. Think of it as select where in SQL. This is the only grouping mechanism in Kubernetes. We do not have service sets. We do not have any other concept of grouping. We just have labels. Because in reality, that cluster picture I showed you before is more like this, where purple is sort of a little red and a little blue, and orange is a little yellow and a little red, and green is a little blue and a little yellow. So I can select all the things that have red, I can select all the things that have blue, and I can select all the things that have yellow, and note that orange is yellow, right? So this helps you to organize your containers in your cluster. The next big pain point, now you've been successful, you've got your applications out there, and oh Lord, you found a bug, you need to update your software. So Kubernetes comes built in with this concept of rolling updates. In Kube versions 1.0 and 1.1, this was a client-side operation, and in version 1.2, we've made it now a server-side operation, so you can take your hands even further off the controls. But a rolling update is a simple thing. This shouldn't be a surprise to anybody here. You start your rolling update, we create a replication controller, which says how many copies of your thing you want alive, and then you start up a service. I haven't talked about services yet, but I'll get there. Service lets you put a virtual IP in front of your pods. And now I say I'm going to bring up a green version of my application. It starts with replicas 0, while the other one has replicas 3. Note here that the service is selecting for app equals my app. This blue one is providing app equals my app and version equals 1. And over here, we're selecting app my app and version equals 2. So the selector will actually select both of these services, which means that I can now bring up another container, and you've started the transition. Now about 25% of your traffic is going to go to the green service, while 75% is going to go to the blue service. If I'm happy with that, I can bring one down. Right? Now, I haven't wasted too much resources, but I've not had any outages as far as my users are concerned. Repeat the process, and you can see very easily how you've done a rolling update with no user visible downtime at all. This is a pretty fundamental part of the system, and it's something that every container orchestration system has to deal with. So in the 1.2 release, we have a new object called a deployment. A deployment is, in effect, updates as a service. Instead of it being a client-side operation, you now have a server-side thing that you can feed a bunch of information about the strategy and the delay between pods and the max overcommit and the, et cetera, which will now do your updates as to your parameters. If you decide halfway through your service, through your rollout, that something's going wrong, we have a very simple command line that says, stop this update, and a very simple command line that says, roll this update back. So you can kubectl undo and go right back to the previous version you were in. Nice thing here now is it aggregates stats. You can actually have multiple updates in flight, so you can do multiple experiments with your application. You can pause it halfway through, so you can have all sorts of combinations of new stuff rolling in your application, and it's all done from a single interface. So I have some live demos. Anybody want to see live demos? Yes? All right. Let's tempt the fates. All right, I have here my GCE cluster that is running. And I'll show you, that it is running by getting a list of the nodes that are available in my cluster. You can see I brought it up about 2 days ago, and I've got 3 nodes in my cluster plus a master. So I have here a bunch of canned demos. I can't type and talk at the same time. I just keep flubbing it. So they're self-typing demos, but I promise that they are real demos that are really running against my real cluster. So I'm going to show you how deployments work. Is that font big enough? Bigger, smaller? How about that? We'll see how it works. So the first thing you'll see is I'm looking at this file called service.yaml. Service.yaml is that red box that was at the top of the picture. Here I'm deploying in the namespace demos. Oh shoot, I didn't do the setup. Let me do the setup first. Sorry, so here my cluster has 2 namespaces right now. Namespace is a way to carve off a private slice of my cluster. So here you're going to see my YAML for a new namespace. And I'll go ahead and create a new namespace. And now you can see that I have a namespace called demos, which is 2 seconds old. Let's try that again. All right, so here is my service. So it's going to be created in this demos namespace that I just carved off for myself, and I call it deployment demo. Specifically, it is listening on port 80 on TCP, and it's selecting any pods that have the label demo deployment. So go ahead and create it. And so now I'm going to go ahead and create some pods. You can see here that, I'm creating a deployment object. It is called deployment demo. It has a selector for demos deployment, same as my service. I'm going to create 5 replicas. It's going to do a rolling update with a maximum surge of 1, so I can only go 1 over my limit as it does the rolling update. And get down to, this is what it's actually going to run. Note that I have demo deployment version v1. I'm going to run 2 containers in my pod. Container number 1 is called BusyBox, and all it does is echo its host name and the string v1 into /data index.html, and goes to sleep. Then I'm going to put a volume called content at /data. Container number 2 is nginx. You can guess what this is doing. It's going to serve user share nginx HTML, which is going to end up being that same index.html file that I just wrote. Very simple. So I've now created my deployment. And you can see in the middle, what I'm doing is I'm actually connecting to that service, and I'm going to attach to it once it connects. Come on, SSH. Well, let's try it. So there we go. So it's connecting to this, and it's going to get, well, it's going to get all the host names that it's running on, and it's going to all say v1. So in the top window, I'm going to start an update. And I'm going to roll my update up to v2. So you can see here we've gone from 5 to 4, 2 to 3, and you can see my update is starting to happen now. You see the v2 is popping up. Now, if I decide halfway through, like, holy cow, that was wrong, I'm going to quick stop, and I'm going to undo it. And you'll see now that the whole thing rolls backwards. Now, I have cranked all of the timeouts on this way down. So you would never do it this fast in reality, but it wouldn't be very interesting if we sat here for 20 minutes waiting for it to update. So you can see now I've aborted my update, and I've gone all the way back to the beginning. And that's it. That's demos. The point here, imagine it's you who is 2 o'clock in the morning and your application has just crapped the bed. You can roll it back with 1 command line. I was asked to take questions at the end because the mic range is a little funky, so we're going to take questions at the end. And I think people are going to line up on this side to do questions at the end. Please ask me hard questions. So this is deployment. Next pane, high availability. Who here does not want high availability? Jesse does not want high availability. So one of the things that we did not do at the beginning of Kubernetes that we heard loud outcry from users was we didn't support multi-AZ clusters from the beginning. We thought, well, you can run multiple clusters, and there's other workarounds. It'll be better this way. Trust us. It's not how we run inside Google. It turns out that what we do inside Google doesn't always apply to the real world, and the outcry from users was unmistakable, so we have added multi-zone clusters. You can now run one cluster across multiple failure zones in clouds like Google and Amazon so that if one zone goes down, you're not going to lose your application. So what happens is we bring up nodes, we label the nodes with which zone they're in, and we automatically try to spread jobs across zones. If a zone goes out, the scheduling system will move all of the jobs to available nodes. Since those nodes are gone, it will bring them up onto the safe zone. When the other zone comes back, you can start to rebalance. This presents to you as a user 0 API changes to Kubernetes. It's just built in, it's out of the box free. We also label things like persistent volumes so that if you have persistent data, you can reattach to your data, you land in the same zone, those sorts of things. This was launched as part of Kubernetes 1.2 about a month ago. The next pain point to talk about, load. Who here thinks you're really ready for your peak load? Right? You run a popular web service, and then Prince dies. and your popular web service that was sharing photographs of prints suddenly gets slammed, right? What do you... Oh, too soon. I'm sorry. You need to react, right? Now, today, the state of the art is sort of human time, right? Somebody gets paged and says the load is too high. They wake up at 2 in the morning because it's always 2 in the morning, and they go to their cluster and they say, oh, add more VMs to my application. If you're really good, you're using some of the auto-scaling features of the various cloud providers, and you get auto-scaling of VMs. We can now do this in Kubernetes with pods. Today, we'll do this based on CPU utilization. We have support for custom metrics in alpha right now. So what it gives you is the ability to scale down when you don't need the capacity, gives you efficiency, and scale up very quickly when you do need the capacity. Obviously, this is not unlimited. You give us min and max bounds, and so we don't blow out your credit card. But you just set this and forget it. I have a demo of this one, but it takes a little too long, so I'm going to skip that demo. But I'm happy to show people afterwards. I have maybe 15 demos here that I would be happy to do. So another piece of pain. Now you've got this cluster out, and it's reacting to load, and it's scaling itself, and you can update it. But you got these things you need to run on every node. Maybe it's your logging agent, or maybe it's your data, your monitoring collector, or maybe it's some important workload that you want to consume the extra storage, but you really want to run it one time on every node. Or maybe you only want to run it on some nodes, right? So we have a new concept called a daemon set. And a daemon set is sort of like a replica set, except it only runs on a specific set of nodes. How you choose which set of nodes is, in fact, a label selector, just like everything else in the Kubernetes system. So what this gives you is the ability to use familiar tools, familiar patterns. It feels like a replica set, but it's, in fact, managing you in a different way. So one of the core principles of the Kubernetes system is that each concept should do one thing. This is why we get dinged for having so many concepts. So let's do another demo. All right, so you can see, well, you can kind of see here, all of my nodes. This is the map of all of the labels that I've applied to the nodes. If you are very astute, you can see that there is no label in here called color. So I'm going to use the color label as a way of setting up nodes. So you can see here, again, I'm going to set up a service. This service is called daemon demo. It again is on port 80, and it's selecting for demo daemons. So I went off and created my service. Now I'm going to create my daemon set object. You can see here again that I have my specification and the label as demo of daemons, and the selector for nodes is color red. I'm only going to care about red nodes. And again, containers, I'm going to run this container called serve hostname. All it does is, can anybody guess? It serves its own hostname on HTML. HTTP rather, sorry. So go off and I create my daemons. Now, I'm going to describe my daemon set. And what describe does is it shows you sort of human-friendly information. What you can see here is the node selector color red, and I have currently number of nodes 0 and current number 0. So I've desired and current 0, because none of my nodes have the red label on it. Let's flip back to tmux. And in the bottom, I'm going to just start connecting. And what you should see is a timeout, because there are no pods satisfying this daemon set. So in the top, I'm going to color each node. So the first node has now been colored. You should see it within a moment. There you go. And now you can see here, desired 1, current 1. And we can repeat for the next minion. And we'll see desired 2, current 2. And any minute now when the Wi-Fi lets me through, it'll start selecting for the second node. Well, let's push ahead. So I'll go ahead and color the third node. Oh, there we go. And you can see now I've got number of nodes 3, current number of nodes 3. Oh, 1 failed. Proof that it is a live demo. I'll have to investigate that afterwards. I'm not apt enough to live debug it in front of you. But you can see here now that you can take this to run Datadog or sysdig or Splunk or whatever favorite tools you've got that need to run on your VMs. You can run one copy on each VM, but you can manage it through Kubernetes. You can use resources through Kubernetes. You can control what is possible in terms of packing onto the machine, all in one console, in one API. Let's do that. All right, so Lee made this a point in a couple of his presentations this morning, node maintenance. This is another thing we didn't really do at the beginning of Kubernetes, but we heard loud and clear that people needed it. So we now have an API through which you can drain a node. Amazing, isn't it? Through kubectl drain, what it will do is it will go off to the machine, it will mark it no longer eligible for scheduling, and then it will one by one kick the jobs off that machine. As it kicks the jobs off, the scheduling system will wake back up and it will put them onto machines, but it will no longer consider that machine as viable for those jobs. You can allow grace periods so your applications can terminate gently, and then it will go off and just do all the work for you. Now you've got an empty machine, you can upgrade your kernel or upgrade your distribution or whatever it is that you need to do with that machine, replace the hard drive probably. And then when you're done, you can tell the system to uncordon that machine. Uncordon means let it start scheduling again. And then the node rejoins the cluster, and everybody's happy, and things go on the way they were before. I do not have a demo of this. All right. Now, we're getting into the fun stuff. So Kubernetes comes built in with a load balancer. The load balancer is a virtual load balancer. It is an L3, L4 load balancer. People cried out in pain, what do you mean it's not an HTTP load balancer? So we give you HTTP load balancing. We've introduced this object called ingress, which is an L7 load balancer. Today it's HTTP and HTTPS only. In the future it will support other higher level protocols. What it lets you do is it maps your incoming HTTP traffic to multiple services on the back end. So you can say host foo.com goes to the red service, and bar.com /A goes to the green service, and bar.com/B goes to the blue service. You can then manage these services independently, right? Maybe one of these is your auth service, and you share your auth service across all of your applications in your fleet, but your separate web app has separate other backend services for it. You can now manage these components independently. This is a fundamental part of the way Google runs things, and I'm embarrassed that it took us so long to get this in Kubernetes. I'm sorry. The interesting thing about ingress is it's an API without a concrete implementation. Kubernetes defines what it means to describe an ingress, and then one of the plugins that you run in your cluster satisfies that ingress. So if you're running in GCE, you run the Google Load Balancer controller, which will watch for all ingress objects, and every time a new ingress object pops up, it'll create you a Google Load Balancer. If you don't like the Google Load Balancer, or you don't want to pay for it, you can instead use HAProxy or Nginx or ... There's a half dozen of these things that are in development right now where people can actually extend it in their own ways. What's really interesting here now is once you move beyond HTTP, you can provide load balancers that support different kinds of protocols. gRPC, pick your favorite application protocol, and you can support load balancing at the L7 application layer. New in Kubernetes 1.2, we added SSL support to the HTTP version. We have all of these implementations in progress and more. I'm happy to talk to people who have ideas about what they want out of L7 load balancing. This is an area of active development right now, so we're leaving it at beta in our 1.2 release right now. That doesn't mean you shouldn't use it, though. Next, configuration. So who has read the 12-factor website? Everybody should read the 12-factor website. It's like the Bible, right? 12-factor, one of the fundamental tenets says configuration comes from your environment. You don't bundle configuration into your application. It's a recipe for having to rev your application and retest it when you don't really need to do that. In this case, we call Kubernetes the environment. So we say we will happily inject configuration for you. So we've introduced this concept called a config map. It's an API object, but it's basically a map of string to string, which lets you store configuration data in our API. And then when you go run your application, we will late bind that into your app, and we will expose it to you either as an environment variables, which you choose, or we'll bind it in as a virtual volume, and we'll store it on the file system for you. And then you can watch those files. You can use FS Notify or your favorite other tools, and watch that application for changes. We will live update that application configuration for you, underneath you, if you want us to. Just go to the API and change the object, and we will automatically populate it out to your applications. Now, you can store the map of websites that you need to serve, or your favorite dirty words, or whatever it is that you're filtering out from your application. You can store it in our API. The logical extension of this is secrets. Right? You don't want to build passwords into your containers, so we can also inject secrets. We made them into two separate API objects so they could have different policies applied to them, but they're very fundamentally the same. So let's do a demo of secrets. OK, so what you see here is my YAML for my secret that I'm going to create in our API. It's of type opaque. We have a couple of built-in types that we use as decorations to understand how to handle it better. In this case, it's opaque. I'm setting the username and the password. Those are base 64 encoded so that I can store binary data in there. That's not encrypted. It's just base 64. And I'm going to go off and create that in my API server. OK. Now, I'm going to go off and run a pod again. In this case, I'm going to run busybox, and all I'm going to do is sleep. And I'm going to mount in the my password, which is a volume of type secret, and it's going to mount the secret that I just created. So I went and created my pod. You can see now that my pod is running. It's 4 seconds old. And I'm going to exec into my pod. So this is sort of like SSH, but you don't need to run SSH inside your own container. So now inside my pod, I have a shell. Oops. So /data is where I put those passwords. So now I have my username. If my application wanted to update, to know what username to use to talk to the database, for example, now it's going to use my username, and my password is also there. I shouldn't show you that. That's it. It's really simple, right? But now you don't have to inject it as env variables directly in your Docker files. You don't have to stick them as env files when you Docker run them. You can late bind these things together. If you want to rotate your keys for secrets, it can be as simple as bouncing your application and it will get the new version of the password. In a future version, we will actually update secrets the same way we update config maps. We've got 7 minutes left. So let's talk about security. Who doesn't like security? Good. So one of the things that's coming up in Kubernetes 1.3 that we've been working on is the idea of network isolation. This lets you describe the directed graph of your application, who's allowed to talk to whom, and it will then allow you to enforce it at the network level. So we have a couple of different implementations from the various network providers. This is the result of a bunch of work through our network special interest group, where a bunch of vendors and users have gotten together to really argue about the right way to do these things and to describe them. We've got an API that we hope to have beta in the 1.3 release in a few months. What it lets you do is things that are important, like block east-west traffic. There's no reason that my front ends should ever be talking to each other, right? There's no reason that my front ends should ever be talking to my back end either. It should only be talking to the middle tier. So you can then implement this at the L3 IP layer, or if you're using a SDN, you can implement it at the SDN layer. However your network chooses to implement it, this is, again, the API that is implemented by plugins. So enough pain. I want to talk a little bit about how awesome Kubernetes is, because that wasn't enough. So I want to say thank you to everybody who has used Kubernetes, who has sent us a patch, fixed our documentation, filed a bug. You guys are amazing. We are in right now the top 0.01% of GitHub projects. In fact, as of this week, we are in the top 100 projects in terms of stars, top 100 of all of GitHub, which is just amazing to me. We have 800 plus unique contributors in less than 2 years. We have 1,200 projects that are building on top of Kubernetes. Just some of the companies, just the ones I'm allowed to talk about. that are contributing, that are using Kubernetes. It's amazing. It kills me when I look at this slide. So thank you to everybody who's participated. As a glimpse of what we've been up to, you can see we're doing about 5K commits between releases, so well over 1,000 commits a month. We had, in this last release cycle, we grew our unique contributors by 50%. We are doing awesome. I'm super happy with the way things are going, but we need to get better. We need to keep growing it. Coming to the OpenStack Summit has been humbling already, and I've only been here for a day. Talking to people who have real problems that they're really trying to solve, I'm just so excited about that. So this is my call. Kubernetes is open. It's an open community. It's open ideas. If you have something that you think we should be doing that we're not doing, I need you to come and talk to us. We are very open to adapting our design. We started with some ideas from Borg, but we know that what we're doing internally does not always map to what you guys need. So please come in and talk to us. This is how this system works, right? Now, I have more demos. No, I'll stop. I'll stop now. I'm about 4:30 short, so let's do questions. Who has questions? Come on, hit me, hit me.
All right, so I'm standing right next to this dude. So anybody have any questions they want to ask? Oops. Come on up. I can't move the mic that far.
I'm happy to talk about other topics that I didn't cover in this talk too. If you have questions, I just accidentally peeked forward and I forgot that I put the scalability slide there. So I'm happy to talk about those sorts of questions too.
So thank you very much for the talk. That was great. I've got two questions, one technical and one not so technical.
Okay.
The technical question is that for applications that are already there, such as Nginx, MySQL, even OpenStack, or like applications, OpenStack is an application which have passwords inside their configuration files. What's the mechanism to deal with that? Using the Kubernetes API as opposed to, I guess, the green application. So that's a technical. The non-technical question is, and I would like a straight answer, do you think is Kubernetes going to replace OpenStack?
Okay. So the technical question is, what about config files that have passwords embedded in them? That then becomes a question for you to decide how you want to manage it. I would put it in a secret and rather than a config map because it is more secret-ish. I hope that over time we can evolve these things and evolve software to separate these two concerns because they really do warrant different management policies, right? One will be encrypted and stored in perhaps hardware security modules in the future, and hardware security modules are expensive and have a very small amount of space, so you need to split these two concepts apart. Do I think Kubernetes will replace OpenStack? No, OpenStack provides a very valuable service, first and foremost in the management of infrastructure, that Kubernetes does not and will not provide. This is not what Kubernetes is about. We are not going to build hardware management systems. We are not going to build network control planes. We want to use those things. We want to integrate with those things, but we are not those things. And we try to draw very clear boundaries around what Kubernetes is not, in part so that we stop the fear, in part so that we stop people sending us pull requests that we're not going to take, and in part so that vendors and partners and other people who are innovating and developing can know that we are not going to step on them when we decide that looks tasty and we want to eat that cookie, right? Other questions?
Anyone else?
Are there plans to use Kubernetes internally at Google?
Are there plans to use Kubernetes?
Or are you already using it?
Are there plans to use Kubernetes inside Google? It depends on what you mean by plans. I have a plan. It's a 5-year plan. The systems you've got inside Google, like Borg, are 12 years old, more than 12 years old. They have literally thousands and thousands of features. Every one of those features is in use by somebody at Google. Trying to take away features was a previous project of mine. Really, really hard because there's no significant features that somebody isn't using. Now, even those features that we think are pretty much do-nothing features at this point, we can't convince people to stop using them because they have to then allocate time to test without those features, et cetera. So replacing Borg is a very tall order. I think it's possible on the order of 3 to 5 years, but not as a replacement. Google has sort of an all-or-nothing mentality. I can't just bring up one cluster and say, well, if you want to use Kubernetes, you can use this, and if you want to use the rest, you use that. I think what we can do is start to shift people over to our cloud product, right? So we're already starting to see internal Google teams porting their applications. A lot of them are sort of our internal-facing applications to start with. I won't tell you what they are, but let's just say they're important. They're starting to port them over to Container Engine on top of cloud. So you can maybe fast forward a few years, and Borg will have a half dozen customers: search, ads, Gmail, cloud, right? And cloud will then service everybody else. And I think then we can see the evolution of containers and VMs and containers and bare metal, and I think there's going to be a lot of interesting innovation there in the next few years.
You mentioned Kubernetes is not going to get in the infrastructure as a service space, but it seems like it's evolving closer and closer to the platform as a service, so the cloud founders in that. Is there a limit where you stop, or is this the new path of work?
So to repeat the question, we claim we're not going to go into IaaS, but we are sort of trending towards PaaS. It's an correct observation. I think the intention is not to become the next PaaS. We don't want to take that level of opinion. We don't think that there is a universal enough answer to platform. Then we don't really want to service that role. We are perfectly happy being the construction kit for other PaaSes, right? You can look at OpenShift, Deis, Gondor, ... There's a half dozen PaaSes that I know of that are building on top of Kubernetes, and we're perfectly happy with that. Now, which facets of a PaaS get upstreamed and which ones don't is really considered case by case. OpenShift has been a great breeding ground for ideas, and a lot of those ideas we're now bringing up into Kubernetes because they are generically useful. Deployment is a great example of something that was part of OpenShift that we've decided was so useful and so universally wanted that we had to upstream it. But Kubernetes will probably never enter the CI/CD space directly. We're not going to have a concept of build or source tree, those sorts of things, because it's just too disparate in what people want out of that. Other questions?